Good morning, welcome. My name is Steve Astorino, as Kiki said. I work out of IBM, and I'm the VP of development for a bunch of things. Some of the exciting technology around AI, machine learning, which I'll talk about a bit today, and also on the most mature products in the world on mainframe. I actually manage some of the products on the mainframe, like DB2 and so forth. So very exciting. And Dean, I'll let you introduce yourself.
Yeah, I'm Dean Wampler from Lightbend as well. I have a made-up title, VP of Fast Data Engineering, because when you're a small company, you can do that sort of thing. I actually run our Fast Data Engineering team that built the Fast Data platform that we'll talk a little bit about today.
Cool. So let's get right into it. So we're going to talk about a few things. We're going to talk about data itself, some of the data strategy, and we're also going to talk about how we're going to leverage, obviously, the Fast Data platform, reactive environment, with also machine learning and AI as being a core component for everything that we're doing in analytics. So if you look at this slide, it really talks about, this is what we call a maturity curve of where we find a lot of our customers are. If you look all the way to the left, it started many, many years ago, how to leverage data, what to do with data, and it really started with operationalizing, automation of data, automating tasks, and making sure that efficiency came through. So that's where we were. It evolved over time into what was called warehousing and BI, being able to get insight out of data, business intelligence, and so forth. It was very exciting at the time. Warehousing is still a very important part of our data strategy, still there today, and it will continue to be there as well. But as we try kind of move on to the right, if you look at the slide, really where we want to get to is self-service analytics. So some customers are already doing that today. You really want to be able to drive insight out of your data on your own, self-serve, and integrate that in your applications. But really the end goal is to have a new business model, transform the way you do everything. Transformation is a big deal these days. New companies are starting up from scratch with all the access to the data, with all the simplicity of the cloud and everything else. It's very easy to disrupt these environments. So really, you want to be the ones that are doing the disrupting. And that's really the end goal. So with event-driven machine learning and analytics on that data in real time as much as possible is where we want to get to. Most customers right now are right in the middle. As you can see, there's different maturity levels. But that's where most of our clients are. So we want to shift you to the right as much as possible, and that's what we'll talk about today a bit. So analyze insights on demand and at scale. Well, what does that really mean? Being able to generate insight as the data is coming in real time as much as possible is very key. Depending on what your use case is, you want to be able to generate that value immediately. There's a study by Forrester that shows the longer it takes for you to make a decision or take an action on your data, the more time goes by, the more likelihood the outcome or the action that you've taken is going to either be the wrong decision or is going to have a negative impact. So that's very important to understand, right? So that's why you want to be able to do things in real time. When we talk about big data, IoT, these large, massive environments with mobiles and everything else, being able to do that at scale is critical for you to succeed. So we're not talking about a small warehouse. We're not talking about a single database. We're talking about a massive scale out of data. And this is also where the Fast Data platform is very valuable, which Dean will get into as well. So I talked about machine learning. Everything we do around machine learning, everything that we do around analytics, in my opinion, requires machine learning. So this is new. How many data scientists do we have in the room here? All right, I see a few. Cool, excellent. So I'll talk a lot about this in this presentation because I feel it's the core of the future, where we need to go, and how if you look at that maturity curve, how we get to transform. And again, in real time is a key to this. So being able to do machine learning in real time is going to be a key contributor to the success of your project, right? So let's pick the most common example for, let's say, a credit card company or a bank or whatever. Fraud is a big deal for them, right? They lose a lot of money every year on fraud. Being able to do AI and detect fraud, stop it from happening in real time, would be a huge key contributor to having that transformation, right? So there's business rules-based solutions right now and so forth, but bringing AI into the picture in real time, if I can detect as it's happening or even predict before it even happens based on conditions, historical data, and transactions that are happening or not happening and so forth, the machine learning algorithms are smart enough to be able to detect that. And that's really where you want to be. All right, so we're going to talk about a few use cases on how the fast data platform is being leveraged. Some are real customers, and I'm not going to talk about who they are, but I'll talk about the use cases. So the first one is a satellite company, and they have satellites, obviously many, many satellites in space. Each satellite's cost them about $400 million, okay? And they have basically a team of engineers that manages these satellites. And what they do is, obviously, this is a true IoT case. They have sensors everywhere. They need to make sure that their satellites are up and running correctly. They need to make sure they're staying the course. With the orbit of the moon and everything else in space, the satellites will shift. So they have to make sure they're staying in a specific location within range. All of that is happening. Data is being sent down to Earth. They're doing maintenance as well on the satellites remotely from Earth as well. They're also installing new satellites, which are going to drive 10 times more data than it does in the current satellites that they have. So you can see that they need a platform that is obviously can handle the fast ingest, the volume, and also be able to do analytics and machine learning as this is happening. So what they're doing is they're leveraging this platform to really drive, excuse me, there's two things that they're trying to achieve. As they're bringing data in right now, it's a manual effort. They load it into spreadsheets, they load it into MATLAB, and obviously that's tedious work. They need to do a lot of analysis. It's a lot of manual effort. There's a lot of cost. The other thing that happens with that is there's a lot of, excuse me, false positives, they call them, which basically they want to keep their satellite in a range within a specific location. And what happens is when they download this data, they're trying to detect if it's within range or not. A lot of the time it's false negatives where it's actually in range, but they thought it wasn't. So there's a lot of time spent, a lot of work spent doing that, which is not necessary. So with the use of the platform and machine learning, they're able to go from a reactive mode to a predictive mode. They know they can predict when it's going to go out of range. They can predict when maintenance is required and so forth, and it's all done automatically. It's a huge cost saving to them, and it's a huge benefit. It's transformational. So that's a great example. Let me talk about another one. So this one, I'm sure you guys have all heard of Watson, IBM Watson. So one of the areas that IBM Watson has been concentrating on is around cancer treatment, oncology with cancer patients. So we have a great story, and this is all, again, it's about volume of data, how much data is out there, being able to bring the data in, analyze, generate insight out of that data. So in this particular example, there was a hospital in Japan, and there was a patient which was obviously had cancer, leukemia. They had tried different types of treatments, chemotherapy and so forth, radiation. And after many, many attempts, they had basically realized that the patient was not responding well to the treatments. And unfortunately, they had told her, look, there's nothing else we can do. We've tried everything. You have a few months to live. As this was happening at the hospital, there was another part of the hospital that was actually working on bringing Watson into the hospital. And one of the value propositions of Watson is that it can consume data at a super high rate compared to a human, for example. In the cancer space for oncology, there's thousands of articles that get published every day. Now, think if you're a doctor, there's no way possible that you can consume all of that data as a human every day. And there's, like I said, thousands a day. So that's where Watson comes in and can actually consume all of this data. And what was happening is, as they were feeding these articles into Watson, and Watson was learning and educating itself, the doctors brought in the case for this patient, the leukemia patient, and ran it through Watson and asked Watson, what is the right cure for this patient? Interestingly enough, Watson had identified a case study that was published in the United States a year earlier, where it had very similar symptom, very similar proposed cure on a new drug that was being released. They went back to the patient and obviously asked, look, there's nothing else we can do, but at the same time, we've been bringing in Watson, working with IBM. we figured out that there's this, Watson has come back with this proposal of this new drug that you could try. Are you willing to try? Obviously, as the patient, why not? I got a few months to live. What have I got to lose? Sure enough, that drug actually was able to save her life. But if you think about the end-to-end story here, it's all about the amount of data that exists out there, having the right platform to bring that data in, generate insight and analyze that data, and then derive an outcome that is going to be successful. So to me, it's a great story. It's a true testament of what Watson and our fast data platform can do as well. All right, so those are a couple examples. I'm going to pass it to Dean. He's got a few more he's going to share.
Okay. I wrote this report a couple of years ago that describes sort of a universal architecture for fast data processing, the kind of things you have to consider when you're evaluating tool choices. It looks at some of the particular tools like Spark and Akka Streams and so forth as possibilities. I actually just updated this, the second edition, so if you liked the first edition, you might want to download the second one. If you hated the first edition, you might want to try the second one, see if it's any better. But anyway, so some of the ideas that I'm going to talk about are derived from this report. Pressing right, yeah. I wanted to talk about a couple of our customer cases. I'm really going to focus on the one on the left, Hewlett-Packard. This was a predictive analytics scenario where they were they acquired a company called Nimble Storage, one of these network-attached storage device vendors. And they were doing predictive analytics on the telemetry coming from these systems to try to anticipate possible failures, like hard drives that appeared to be on the verge of failing, and then take preemptive action to prevent any sort of customer outage. Really, the other cases are kind of similar when you get down to the architectural level. The Starbucks case was replacing the infrastructure around their point-of-sale systems. Whenever you go into Starbucks, use your card or whatever, as well as supply chain management. Royal Caribbean is obviously a big cruise line. They were doing work on what they called real-time personalization, which is kind of knowing what you want, what you're interested in at the moment that you're engaging with them online so that they can direct you to the right services. I mean, Capital One has been a really interesting story. They do things now like almost instant auto loan approvals. You can be in an auto dealer with your phone and get an approval very quickly. The last time I bought a car, I had to go beg the bank for a couple of days to convince them that I wasn't a risk. Somehow they believed me. But now I wouldn't have to do that. And they also do a lot of work in real-time analysis of data, all based on the idea that, if we're going to actually leverage all the things that Steve just talked about, the most impactful way we can leverage those things is as soon as possible. And that kind of forces us to process data as it arrives whenever we can, leveraging historical data for context. But also it forces us to integrate that data processing with the rest of our environment so that we can leverage those results back with the customer as quickly as possible. So I'll talk a little bit about the architecture for doing this. Specifically the HP case where they were modeling the behavior of these devices and then doing predictive maintenance whenever they detected problems. So I'll come back and go through an architecture for how you might do this in a few minutes. Back to Steve.
All right, so I'm going to share some results of studies that Forrester has done around the importance of data and the type of data. So interestingly enough, in a recent study shows that mobile and IoT data is become more and more critical in different organizations. And that actually makes sense when you think about it. So they did a study on how critical, either a critical priority or high priority for different types of data. So they did that for mobile sources. And you can see on the chart, 23% consider it critical, another 52% consider it high priority. So in total, 75%. Similar thing for IoT data is also 75%. And interestingly enough, that has now just slightly surpassed your traditional data sources if you think about your OLTP data sources or warehouses and where your traditional data is. That's very, very important to understand. It's key because as you can see what's happening out there with all these mobile devices, all these different applications that are built on devices, all these, even the satellite case that I used about IoT, IoT data in cars and in any device really, and being able to leverage that to better your business models, generate insight out of that that can transform the way you present your services or you provide services to your customer. That is a huge deal. And what this study is saying is that mobile data and IoT data is now actually more important on your transactional data, your typical OLTP data, client data that you have from the past. So it's not that it's not important anymore, but mobile and IoT has now eventually surpassed it. So that's pretty exciting. It's good to know, and it's very important that we put that into our strategy as we're looking at this, right? The other study that was done is really ask customers, how are they considering kind of refocusing or revamping their data strategy over time. And 87% of them said yes, so that's great news. But then they also went into other questions, and basically 9 in 10 organizations said that they require fast ingest data as well as being able to analyze that data in the same day. Okay, you can call that real time, but even to get into that realization is a big deal because right now there are companies that are doing insight on their data weeks later, right? If I go back to that fraud example I gave, I'm detecting fraud that had happened a week ago or a month ago. It's not very useful anymore. It may lead me to help in an investigation, but it's way past, it's too late, right? 50% of them feel that they have a missed opportunity if they don't act on that data. That's a huge percentage as well. 41% of them feel it's gonna negatively affect their customer experience. That's also a big deal. 37% are concerned about more frequent down or longer downtimes in their environment. That's also a huge deal, right? Every time there's an outage, it costs millions and millions of dollars, depending how complicated your infrastructure is. 36% of them are concerned in falling behind, and 35% feel they're going to lose a competitive edge. So if you think about all of these statistics, the transformation needs to happen now. This is what this is telling you. So you definitely should be looking at your data strategy and making sure that you're figuring out how to use a platform like Fast Data Platform to improve your business. The other one, another study that was done, it was around machine learning. So I talked about machine learning, and there was several questions that were asked, being able to do machine learning on stored data as well as streamed data, right? And to me, they're both very valuable. Machine learning can and should happen everywhere at any life of its data cycle, at any point of its data cycle. So some of the questions were asked, how many were currently use machine learning? So if you look at the first statistics, 45% of them are using that on streamed data, 33% are using it on stored data. That in itself is actually interesting because it tells you that being able to do machine learning as the data is coming in, it's actually probably more valuable, and this is showing that in that statistic. The other one is the question was asked, how many of you are planning to use machine learning, right? So you can see the statistics there, 32 and 40%. But anyways, altogether, you're above 70% for the ones that are either using it already or planning to use it in the near future, right? Then there's 16%, 24% who are discussing the use of machine learning. And then there's a small percentage at the bottom who have not thought about it, don't plan to talk about it. Well, I kind of feel bad for the last two at the bottom, because if they're not looking at machine learning right now, they're definitely going to be left behind. So so Dean's going to talk about some of the architecture of this platform. So let me pass it back to him.
So I did big data consulting for a while in the Hadoop space, and if you're a data engineer in that world, what you would worry about is keeping your HBase and HDFS file system healthy. But as far as the analytics, what would be the analog of microservices on the other side? Usually they were like Spark jobs that would run for a couple hours and then they'd be done. Not, challenging enough, but not that difficult to keep healthy. But if you convert those to streaming jobs, you sort of raise the bar on the operational challenge, because now you have something that's going to be running for days or weeks or months. And if you run something long enough, inevitably you'll see every possible rare thing happen to you, such as network partitions and hardware failures, spikes in traffic and so forth. So it's forced the big data kind of engineers to learn the techniques that microservice people have been perfecting for a while about achieving these reactive principles of availability and scalability, durability, and all that. At the same time, if you start building microservices and your organization's successful, then inevitably data becomes kind of a dominant concern. My favorite example is Twitter, actually. Twitter started as like this 3-tier Ruby on Rails app that would deliver fail whales, right? That was kind of their business model at first. And then gradually, they accumulated a lot more customers, well, users anyway, and a lot more data. And now, the Twitter infrastructure is mostly giant pipes, at least in virtual senses. So it kind of, I think, is forcing the concerns and the skill sets to merge in the middle as people, on the right-hand side, go more towards I should do it this way, go more towards stream processing. On the left-hand side, as data becomes a dominant concern, we're all having to do the same kinds of things in our systems. So now I'm going to talk a little bit about the details of this. Well, it's not necessarily exactly how HP did this project, but just to give you a sense of one of the ways you could do it architecturally, and talk about a few tools that are involved. So schematically, this is what they did. They have these nimble storage, network-attached storage devices. They're ingesting telemetry to do modeling, to kind of learn to predict anomalies, either by looking for outliers in data or by past behavior. And if something is detected as a potential anomaly, then they trigger some sort of handling of it. Oh, and I forgot this. I have this little build. It just goes through what I just said. So here we are. So this picture is actually taken from the report that I mentioned earlier. I'm not going to go through it in a lot of detail, but just to give you a sense of what's involved here in tying all of these pieces together in a streaming context. There's actually 3 major pipelines, if you will, happening here. The first one is model training. And the way I decided to sketch this out is suppose that we ingest our telemetry into Kafka is like our data backplane, really highly available, highly durable. Most of you have probably used Kafka or at least heard of it. You can categorize data by topics. You can have as many producers and consumers per topic, all kinds of good stuff like that. But what we're going to do now is ingest this into Spark, because Spark is very good at handling very big data sets. And oftentimes, when you train models, you have to pull in a lot of historical data, not just the current data that you're working with. So in a streaming context, you have this problem that periodically your models are going to grow stale over time because the world's changing. People are inventing new ways to do fraud, to do spam, and so forth. Systems start failing in different ways under different kinds of load and so forth. So periodically, we're going to retrain our models, and that'll be the arrow going to the right to Spark. The arrow going back the other way would be the new model parameters, whatever model we're using. We'll write those to a new Kafka topic. We'll use that as our integration framework. And that way, services don't have to know exactly where data is going or coming from. They just have to know how to talk to Kafka. So we'll write those parameters back to Kafka. And the second tier then would be the actual serving of the model. Here we've got 2 streams of data going to the right out of Kafka. First, it'll be the same raw data that we used for model training, but it'll also be these updated model parameters that periodically show up. And the magic on the right-hand side will be to integrate those new model parameters into a new model instance and then start scoring with that in real time. Meanwhile, scoring with whatever the last model was. Now, the reason I picked low latency microservices with libraries like Akka streams and Kafka streams is maybe not so much in this particular example, but often you'll have very low latency requirements. If you're doing like credit card transactions or something, obviously you'd like to catch problems as quickly as possible. And usually you're not dealing with as much data as we had to deal with when we were doing training, because we might just be doing scoring of one record at a time, so all we need is enough space to handle that one record and whatever the model framework is that we're using for scoring. So it's a great idea maybe to embed this in microservices to get the extra flexibility of low latency and various deployment scenarios. Now, if we actually detect an anomaly in this case, then there is actually an arrow going back to yet another Kafka topic. That would be the occasional report of a potential anomaly, and that would get written again to another Kafka topic. And then the last bit would be just the regular microservices that we would write to manage sessions with these devices. These are doing things all the time, like providing, let's say, language translation or voice services. But also they're going to be used to handle these failure scenarios. So they'll be watching this Kafka topic with reports of anomalies. When one shows up, they'll route it to the correct microservice that's talking to that device and initiate corrective action. And in this case, it might be something like move data off the drive that appears to be failing. That may not even be necessary. It's probably already replicated in the device for resiliency. But you do want to get activity off of the device, off the drive, so that you can shut it down and tell the ops people to service it whenever convenient. All the while, people are using it. Customers never know there's a problem, except maybe a slight performance degradation. But nevertheless, there's no outages. So that's kind of the idea. But I want you to notice that without going into all the details here, we've had to pull in our microservices both for model serving, but also for the regular processing we do, and they need to be integrated in some way with our data systems. And one way to do that, at least the way I've shown here, is that we just use Kafka as our integration layer. And we can mix in as many different kinds of tools as we want to have kind of a uniform environment that services our needs within our latency budget, with our scalability requirements and all that kind of stuff. Back to Steve.
All right, great. So I know we said there was a few data scientists in the room. For everyone else, what I'm going to do is I'm going to try to do a 3-minute course on machine learning. So if I can understand it, I can guarantee you guys can all understand it. But it's good to understand the concepts at a high level, at the very least, to see how we can integrate ML into our applications, right? So if you look at this diagram, it all obviously starts with data. One of the things about machine learning is it cannot be done in isolation. You need a team of different users, different personas to collaborate together to get a successful implementation of machine learning done. So obviously data engineers, you need to work with data scientists as well, and then app developers to put that into kind of a production environment. So if you look at this flow, it all starts with data, okay? So machine learning, the way it works is you have 3 key components. One is your data. Then you take that historical data, you take that data that you have, and you ingest it into statistical mathematical algorithms. So it needs to be prepped, it needs to be cleaned, you need to be able to put it into feed it into these algorithms. These algorithms are then configured with different features, the data that you actually want to consider as part of the algorithm, and a set of different parameters. There's different algorithms can be chosen and so forth. That phase is called the training phase of a model, okay? So you have your data, you ingest it into the mathematical algorithms, you have now trained this data with these algorithms, and the output of that is what's called the model. So if you've heard of people talk about machine learning models, that is actually what gets created. So in this cycle, you start with your data, you feed it into your algorithms, the output is a model. Then you take that model and you put it into what's called into a live system, into a production environment, and that is where an application, a human, some process can call it and execute the model. The execution of that model is called scoring. So being able to execute that model, score that model, and then give you an answer, give you a prediction on what could happen. So, and that is all based on, again, the flow is your historical data, what has happened in the past with those conditions, feed it into these algorithms that will tell you the probability that this will likely happen again under these conditions, and that is how the machine learning model is then created and put into production. Now, it doesn't end there. It's kind of a cycle, right? Because the data, I think, Dean, you mentioned this, the data will continue to change, the algorithms will evolve as well, so you need to continuously do this in a kind of a called vicious cycle where as the new data is coming in, it's relearning based on this data. So the conditions may change, the content of the data are going to change, and so forth. So the model needs to continually update, right? So if we look at some of the tools that we're building, this is actually built into the process where as you put a model into production and you score that model, the new data that's coming in, then it's automatically retraining and then automatically redeploying that model as well so that it stays current and your probability of success is very high. So if I go back to that churn model, or sorry, not the churn model, but the fraud detection model, as an application or as a developer, then you would call that model and basically say, is this fraud or not? As an example, it could be at that high level, and then raise a flag, create a condition, create an alert, whatever, based on the data that's coming in and the detection of the prediction of that fraud happening. So that is what machine learning is at high level. It's pretty simple when you think about it. So there's a few screenshots here of the way we approach. So we have a product called Watson Studio, which is part of the fast data platform. And there are at least two typical users for building machine learning models for data scientists. One is a coder, which I don't have a screenshot here, but it's essentially notebooks is the tool that gets used. There's different types of notebooks, and it gets used to generate, to build models in machine learning. And then the other one is a visual model builder. So if you see on the left here, we have what's called our SPSS modeler view, which is more for non-coder, even line of business users to be able to create a model visually. So you're dragging and dropping nodes, you're doing all your data cleansing, you're doing all your algorithm selection and everything else all through a UI, and then you can collaborate with more hardcore data scientists to work together through notebooks and eventually build a model that can be deployed into production. So this is the tool that we have. It's pretty exciting. Actually, there's a deep dive later on today, which also will cover some of this. The neat thing about, as application developers, the neat thing that we've done as part of this is the simplicity of deploying a model. We talk to different organizations, different banks, big retailers, and there's a lot of business processes in place that unfortunately have slowed down in the past the ability to put models into production very quickly. In fact, we've heard 6, 9, 12 months to put a model into production. So when we take it back to what we talked about real time, that is far from real time. So if I create a model today based on the data that's coming in today and then put it into production in 6 months, that's going to give me the wrong output. It's going to give me the wrong outcome. So it's almost useless, right? So you want to be able to do it in real time. What this screen is a little hard to see, but what it's showing here is that with our tool, you can basically right-click on the model and say deploy. It's less than a second. It creates a web service with REST API, fully authenticated with authentication token, where an application can now call it in real time immediately, fully authenticated and everything else through REST API. So it's pretty awesome. It's really transformational on how simple it is now to do that, as opposed to in the past where you had to go through all these roadblocks to get it deployed into a production environment. All right, so the other one that I'm going to talk about is part of, again, when we look at data itself, part of the solution for the fast data platform is something called Event Store, which is really dealing with the high volume of data. So there are some key critical components to be able to have a successful implementation. One is the velocity of the data. How quickly the data, the ingest, having super fast ingest rates to be able to handle the data that's coming in. That's number one. The volume of data, the petabytes of data that are coming in. As we talked about IoT use cases, we talk about mobile use cases. It's very important that you can handle that volume, right? The performance and flexibility. So you want to be able to, you have all these petabytes of data now. You want to be able to quickly look up the data and so forth. Being able to do analytics as quickly as possible on that data. You want to be able to do analytics while transactional data is coming in at the same time and still provide you high performance. So it's a key ingredient of being able to have a successful implementation. And then also, again, being able to do high fast queries and the analytics in real time, and then being able to share that with other components even outside of the fast data platform. So it's also a key component of that, because once you've done the core work inside the platform, you want to be able to share now, integrate with other applications and so forth. So those are all the key ingredients to be able to successfully have an event-driven application. All right, so Dean, you're going to talk a little bit more about the architecture.
So we talked about a lot of stuff that you have to put together to make things work. So wouldn't it be great if somebody put it together for you already? Anyway, so what I did with my team was we worked on integrating and curating and managing the streaming engine part, and we like Akka streams and Kafka streams as library microservice options, and then Spark and Flink for when you need those big scalable things. Of course, Lightbend is famous for its microservice toolkits, and then Kafka is your backplane. But what we didn't have is like a really solid database underneath, and all of this machine learning, Watson stuff that Steve was talking about. So we put the two together and created the IBM Fast Data Platform that bundles all of these capabilities together. with all the monitoring and management tools you need, the sort of integration testing you would expect, and running on Mesosphere DCOS. So what we hope you do, we'll come and check us out today. In fact, I have some homework for all of you guys since you bothered to show up this morning. I want you to visit our booths and talk to us about what we've got, collect valuable swag. That's really the only reason you go, of course. But Anson and Adam from IBM are going to talk in more detail about building fast data systems at 310 today in this room. And then afterwards, I'm going to do a talk where I'll dive into that second part of the diagram, actually using microservices to serve or process data in the streaming context. That'll be 410 here. And then after that, IBM is throwing a reception and a meetup from 5 to 7 in the International Ballroom 1 and 2 on level 3, something like that. And beer, wine, and light refreshments will be served. Thank you very much.
Thank you.